Okay, students, today we're going to talk about graphing exponential functions. Now, how you can remember if it's exponential is the keyword here. The keyword is exponent. That means the variable is in the exponent. Simple way to remember that it's called exponential. You look for where the variable is, x, and it's in the exponent as we see right here, so it's called exponential. Function, remember, definition of function is it passes the vertical line test. So I draw any vertical line, it's only going to cross one time. Okay. So that means if you try graphing something and you think it looks like this, you're wrong. That's not a function. It fails the vertical line test. All right. The exponential growth function. So there's growth and decay. So in this section right here, this page at least is growth. So as we read graphs left to right, so you notice it's growing as we go left to right. Exponential is also going to grow much faster than linear. Remember, linear is a line. Exponential grows much faster than linear. Just know that as well. It's going to go up much faster. You may think it is going to graph into a parabola, but it doesn't. It's got the curve on this side like this, but it just keeps going down until it gets down to the x-axis. Okay, as we'll read here, that's called an asymptote of the parent function, that is. That's before any shifts or translations, that is, take place. Okay, the graphs of exponential equations can be transformed. Remember, we talk about transformations in geometry all the time. We had your reflection, rotation, translation, glide reflection. By changing the value of the constants a, h, and k in the exponential equation, f of x, remember that means that's function notation. F is the name of the function. It's the f function. It could be c of x, g of x, and that's the g part is just the name of the function. The variable inside is the independent variable, which means it has to be the exact same variable that's on the other side of the equation. Okay, that's what you know to plug in there. Okay, and so the fx is function notation. A is a constant out front, which will, if it's positive, and greater than 1, it's going to make it go up faster. If it's negative, it's going to reflect over the x-axis and have it go down. Okay. If it's between 0 and 1, then it's going to make it not go quite as fast up. Okay. The x minus h, we do the opposite operation. So it means to be h units to the right. And k, we leave it as the same. Okay, because k would normally be over there, and then it'd be f or y minus k, and then it'd be the opposite, but they move it over the right side so that k is the same here. So opposite here for the h, same direction for the k. So it says plus 3, that'd be up 3. Versus if it said x minus 3, then it'd be right 3. Okay, so this goes along opposite, and this is the x direction, because you should recognize x is right connected with the x. So x direction, which is only left or right, and the k is connected with the y across the other side, so it's the y direction, up or down. Okay, so we've talked about this kind of stuff before. You talked about it in geometry as well. We dealt with it with quadratics already. Okay, you still have these same shifts, translations, etc., that you have in quadratics. You have it in all types of polynomial functions. Okay, so this itself right here is called the parent function. Okay, when a is 1. Okay, it's the parent function there. So here we have the parent function right here, f of x equals b to the x. Parent function means the starting point without any translations. So that'd be like a 0 right there and a 0 right there. Okay, and nothing affecting in the front. So that now simplifies down to f of x equals b to the x. Okay. B has to be greater than 1. Okay. If b equaled 1, 1 to any power is 1, so it would be a horizontal line, y equals 1. If it was between 0 and 1, I can write that as a fraction, such as 1/2 is between 0 and 1. Well, 1/2 is the same thing as 2 to the negative 1, okay, to the x, which now is the same thing as 2 to the negative x. And when you have a negative in front of the x, that reflects it over the y-axis. So this would be, if it was f of x equal b to the negative x, that would be the red one right there, reflecting across the y-axis. That's what that negative does up front like this. So for 1/2 can be written as 2 to the negative 1, and remember, power to power, you multiply. So now that equals 2 to the negative x, which tells me then that's a reflection over the y-axis. So that's what would happen if b is between 0 and 1. It's actually, that is an exponential decay, which would be on the next sheet, maybe on the other side or on the next section. Okay, so we're talking about exponential growth. So in order for grow, it has to be greater than 1. Decay would be between 0 and 1. All right, so number 1 here. The function is continuous. Continuous is a term you need to understand because you use it in pre-calculus and calculus. Continuous means I can draw the function without picking up my pencil at all. So for example, if I had this right here, but then I had a circle, because that point wasn't involved in it, that would not be continuous. I'd have to pick up my pencil and move it to the next part. Okay, so that's a non-continuous function. Okay, I have a hole in the graph like this. So continuous means I can write it without drawing it, without picking up the pencil. 1-to-1 is the next key vocab. We've talked about a function. The definition of function is for every x there's only one y, right? We've talked about that before. For every independent variable there's only one dependent variable, or for every input there's only one output. But it doesn't have to be true the other way around. Okay, so for example, that right there, I have 1, 2, 2, 2, and 3, 2. 1, 1, 2, 2, 2, 3, 2. That passes the definition of function. Okay, because remember, if I looked at it graphically, it would pass the vertical line test. So it's only, this is not 1-to-1. This is just going in one direction. For every x, there's one y. Well, 1-to-1 means for every, not only for every x, there's one y, but for every y, there's one x. So this would not be 1-to-1, because for every y, there happen to be 3 x's in this case. So what it means to be 1-to-1 is that it passes, I'm talking about graphically, passes the vertical and horizontal line test. Let's get rid of all this just so I can write horizontal line test. Okay, so this might be the first time you've ever heard of 1-to-1. Must pass the horizontal and vertical line test. So far, functions we've only talked about passing the vertical line test. Well, now you understand it has to pass the horizontal line test too in order for something to be 1-to-1. So when I graph this, it also will pass the horizontal line test. It'll only cross one time on any horizontal line I draw. And it only passes one time on every vertical line for the vertical line test. So if that's the case, then it's called 1-to-1. And it's increasing. And when we're talking about increasing, that means the y values are increasing. Y values. So we're talking about increasing. The x obviously always increases as you go left to right. Okay, there's nothing special about that. That's just automatic. When we talk about increase, that means the y values are increasing. So as I go left to right, every time I go to the right, the y value is getting larger. That's what it refers to as increasing. Okay. So now you've got those three vocab words, continuous one-to-one and increasing. Let's go down to the next one. The domain is a set of all real numbers. Domain means, remember, all the x values that I can put into the equation. So it says the set of all real numbers. The real numbers is the entire number line. It's called the real number line. So that means every x value works. So x is all real. Sometimes you'll see real written like that. Or you can just write out D for domain, all real. Write out the word all real. Okay, if you want. All right, so that's the domain. Versus, remember the range coming at number 4 is all the y values. So it's y, domain, x values. The range is set, we'll come back to number 3 in just a second. The range is a set of all non-zero real numbers. Non-zero real numbers. Let's see here. That is not correct. You can say the range. So again, we're talking about the parent function. I'm not talking about any shifts yet. The range is a set of all positive real numbers. Okay, so it doesn't include. Remember, zero is not positive. You got to remember, zero is a neutral number. So it's all values greater than 0. So you'd say y greater than 0, not equal to 0, greater than 0. Okay, it says non-zero real numbers. That would include negative numbers. It's not true. You're not going to have negative numbers unless there's a shift down. Okay, which takes place, remember, from the k. That would shift it down. But we're talking about the parent function. Remember, the parent function, there are no shifts. And these rules are applying to the parent function, as it says right here, parent function. Okay, so this should have said, if you want to say non-zero positive real numbers, they want to add in the word positive there. Okay, but it's not negative. So you can say they forgot the word positive, or you can just say the range is all a non, just you can say all the positive real numbers. So I say you don't have to say non-zero. You can just say positive real numbers. Okay. That would have been the easiest thing to say, positive real numbers. Get rid of the non-zero and just say positive real numbers. Okay. All right, number 5. The graph contains the 0.01. That's going to always be the case for any parent function. Okay, why? Because any number, b is any number. Of course, we're talking greater than 1, but still it's not going to matter unless it's 0 to 0. 0 to 0 is undefined. That's a huge debate in the math. But anyway, any other number to the 0 power equals 1. You learned this in Algebra 1. Okay, you learned it earlier in Algebra 2. Okay, exponent rules. Anything to the 0 power is 1. Now, if you want a quick little proof of that to see it, say I go 2 cubed. You should know that's 8. 2 squared, 4. 2 to the first, 2. We'll leave the 2 to 0 alone. 2 to the negative 1, 1/2. And 2 to the negative 2, 1/4. Okay, and you could do this with any base. I just chose base 2. Okay, well, except for base 1, you wouldn't use base 1. 3, 4, 5, etc. So what is happening to get from 8 to 4? It's dividing by 2. What's happening to get from 4 to 2? It's dividing by 2. So you notice the pattern is divided by 2. So what's 2 divided by 2? It's 1. And what's 1 divided by 2? 1/2. What's 1/2 divided by 2? 1/4. So there we can see why any base to the 0 power is 1. We can apply that same rule each time. All right, there's a simple proof of why 2 to 0 or any number to 0 besides 0 to 0 is 1. All right, so now let's go ahead. Let me erase all this. You can go back and pause it and write all this down if you haven't done that yet. Okay, so it says graph 4 to the x plus 2 state domain and range. Well, remember here, this tells me it's shifted up 2. So normally I'd have 4 to 0. So this says add up 2 to all the y coordinates that I normally would have. So if I did x and I did 4 to the x, so it'd be 0, that'd be 1. If I did 1, that'd be 4. If I did 2, that would be 16. Well, now I'm doing 4 to the x plus 2. All I'm doing is adding 2 to the y coordinate. So now it becomes 0, 3, 1, 6, and 2, 18. Okay, I just shifted everything up 2 units. Okay, so remember the domain, all real. It's going to always be all real. The range, remember originally the range was y is greater than 0, right? That's without any shift. But what did we do? We added 2 to it. So now it becomes y is greater than 2. We added 2 to every y coordinate. So shifted the asymptote up. Oh, so speaking of that, I forgot to go back to number 3 here. The x-axis is the asymptote of the graph. The asymptote means it's usually a horizontal asymptote, as the x-axis is. Remember the equation of the x-axis is y equals 0. You should know that from Algebra 1, geometry, and Algebra 2. Earlier in Algebra 2. A horizontal asymptote means the number or the curve gets closer and closer to that asymptote, to that line, but never crosses it. Okay, and that's true in most cases. There are a few exceptions where a horizontal asymptote can be crossed. A vertical asymptote can never be crossed. But you usually don't come across those horizontal asymptotes that cross until pre-calculus or calculus. All right. So the normal asymptote, you draw an asymptote, you draw dashes like this, showing it's not really part of the graph. It's dashed, so you wouldn't see it. And the curve will get closer and closer to 0, but never touch it. So by default, the asymptote for the parent function is y equals 0. But remember, we added 2 to it right here. So that shifted it up to, now this one would become right across here, and be y equals 2 now. Okay, so if I plug that in my graphing calculator, I will see it go like that. Now, of course, it's not going to put the asymptote in there for you. You have to know to draw the asymptote yourself. So those of you who are completely dependent on the graphing calculator, you'll be in trouble, because it's not going to show you the asymptote. It'll show you that it gets, close to 2, really close to 2, but it'll never reach 2. But you have to know to write the equation y equals 2 for the horizontal asymptote. Okay. Graph that. So here's the graph of it right here. Okay, so I got 0, 3, 1, 4, 2, is all the way up at 16. Okay. I'm sorry, not 1, 4, 1, 6. 1, 6 right there. And then be up at 216. Okay. You really have to get like a couple, the 0 and the 1, get that one, and just draw your asymptote in first, y equals 2. Okay, so do that first. Write down y equals 2 next to it. Okay, so I know that you know what the equation outline is. And then do it at 0 and at 1, and then go ahead and draw your curve in there like that. The range, remember it was at y equals greater than y equals 0, or y is greater than 0. Now we've added 2 to it, we shift everything up, so now the final answer is for the range, y is greater than 2. Okay. So notice here, they write in the positive real numbers. If they forgot up top there with the non-zero, they should have said positive real numbers there. Okay, now you see them doing it correctly down here. Okay. All right, that takes care of that. Let's go to the other page. And you can put these in a graphing calculator to check that you're doing it right as well. Graphing exponential functions, exponential decay. So as I showed you before, exponential decay is taking the exponential growth and reflecting it over the y-axis. So you see it coming down. It's got the same set domains all real, range y is greater than 0. This is the parent function until you have any translations, shifts with it. Plots at 0, 1. So that one, they messed up the numbering there. So notice this is 0, 1. 2 is actually right there, so 4 is right there. So there's an error right there. So that is actually 0, 1. They put the 2 and the 4 in the wrong spot right there. Okay, so it's again things you want to look for errors. Don't assume the book's always right, because they always think, oh, 0, 2. No, it's 0, 1. Okay, remember, any power, any number 1/2 to 0 power equals 1. So it's going to be 0, 1, unless you had then a shift up like we had before. So 1/2, okay, remember that's the same thing as 2 to the negative 1, as I pointed out before. That's 1/2 to the x, which down is the same thing as 2 to the negative x. So 2 to the negative x is the exact same thing as 1/2 to the x. Okay, so you should know those are the exact same thing. Okay, remember, when I have a negative in the exponent, that means take the reciprocal. The reciprocal of 2 over 1 is 1 over 2, which is what you see right there. That's how you change a negative exponent to a positive. Do the reciprocal. Okay, I've learned that in Algebra 1 and earlier in Algebra 2 as well. Okay, so this is exponential decay, so all the y values are decaying, are going down towards 0 for all parent functions. Horizontal asymptote at y equals 0, okay, which is the x-axis. Domain is all real, range is still. Y is greater than or equal to 0, or not, y is greater than 0, not equal to 0. Okay, this time they wrote it right. All positive real numbers. There you go. They wrote it right this time compared to the other page. Last page there. Okay. So all these graphs should look like that, since the key is the b to the x right here. This is what you're looking for. This b part has to be between 0 and 1 for it to be exponential decay. It's not about this right here. It's not about this 4 out here. That does not make it exponential growth. It's still an exponential decay as long as the b is between 0 and 1. Okay, then it will always be decay. Okay, now, what does this negative do out here? That reflects it over the x-axis. So remember, it would have been coming down here, but now it reflected over the, or gone wider even, okay, come down here, and it reflected over the x-axis. And so that's what's happened down here. Okay, and it shifted right 5. That's right 5 and an up 6. Shift right there. Okay, so if there's a negative out front, that's going to reflect over the x-axis, just so you know. Okay. All right, that will go ahead and end this video.